Hello, class. Welcome to our Calculus 2 lecture for Monday, April 20th. I wanted to remind you that we will have a test a week from Monday, April 20th, and that's obviously April the 27th. And that's going to work very much like the last test. I will post that by 1 p.m. On Monday, April 27th, and then you will, write out your answers and then convert those to scan those and convert those to PDF form, and then email those back to me by Wednesday, April 29th. So Monday, April 27th is the last official class day for this class. Of course, that has a lot less meaning right now that we're conducting things online. But we will not have a lecture for Monday, April 27th. But of course, on that day, Taylor will still hold her SI sessions, and she will talk about the last homework, which is not posted yet. And that will be due on the day of the final exam, which is May the 6th. So if you are taking the final exam will work like the tests have since the break, right? I will post that on by 1 p.m. on Wednesday, May the 6th, and then you can and then you will email that back to me by May the 8th, Friday, May the 8th, and for me to grade, right? And so on this homework list, there's going to be one additional homework. That will be the subject of Wednesday's lecture. So the lecture for April 22nd is one more topic in Series, but that will not be on the test for Monday, April 27th. So the test for Monday, April 27th will only cover through this homework, the first homework on Series, okay? And what I'm going to talk about today, which is the integral test for determining if series converge. Now, speaking of the test, the sample test is posted now. And so the sample test for test number 3 is now posted already on the Blackboard site. I believe our test number 3 starts with trigonometric substitution. So it starts with that section, trig substitution, and then covers up through this homework, 9.2, 9.3 homework, which is due on the day of the test, right? Okay. And so you can see from the problems on the sample test what sort of questions will be on test number 3, right? Okay. But again, we will have one additional homework, which I will post on Wednesday or by Wednesday after that lecture on our last topic. But that is not on the test number 3, and that homework is not due until the day of the final exam, right? Okay. So that's about where we are in terms of homeworks and tests and so forth. So only a couple of lectures left, one today and one for Wednesday. And again, there won't be a new lecture on Monday, April 27th, but Taylor will still be holding her SI session on Monday, April 27th. I'm sure that Taylor will also have a final exam review for those of you who need to take the final exam. Some of you may be able to be excused from the final exam because of your calculus flux totals. I will send you more information about the calculus flux totals and what's required to be excused from the final exam this week. But your calculus flux totals will not be completely updated until after Monday, April 27th, right? When these homeworks are due, and then I get to add in the flux dollars for the attendance policy. So I believe I mentioned before that the flux dollars for the attendance, the 25 flux dollars for the attendance will be based on your attendance prior to the break, right? And then plus your participation doing the homeworks and so forth since the break. Okay, so if you were attending well before the break and then have been participating since the break in doing your homeworks and taking the test, then you will get the $25 plus the $2 that you've been getting for attending Taylor's SI sessions. I have been adding those flux dollars in. Okay, so the flux dollar policy for testing out the final exam is still in effect. However, I will send you more information on what totals are required in your flux dollars in order to test out of the final exam this week. Okay, and in order to be excused from the final exam this week, right? Remember now, if you do take the option of not taking the final exam, your final exam score will be the average of your 3 midterm scores, right? Okay, so of course you want to have a good average on your 3 midterm scores, right? Because you to not take the final exam. Because you don't want to, insert, a poor average there as your final exam score, and then maybe bring your letter grade down, right? Okay, so I think I talked about most of the process issues here of how the class is going to continue for the rest of the semester, which is not much, right? We only have just about a week left, right? And then the final exam from today. Let's see. Yeah, I think I mentioned most of the things I needed to say. Except I'm sure Taylor will have a review for exam number 3 that will probably be, I'm guessing, Wednesday, April 22nd, right? Okay, will be her exam review, but I'm just anticipating that. So Taylor will send you a separate message about when her exam review is going to be held for exam number 3. Okay, I hope everyone is doing well. Most people are again continuing to do well on their homework. I know we had a little snafu on the improper integrals homework. I had unfortunately a prior version of that got posted automatically that I wasn't aware of. I had edited that homework, however, to shorten it. So I had to take down the prior version and then put back up the edited version. And I know that caused some people to repeat work, so I apologize for that. But the new version, the second version, was much shorter than the original version of the assignment. Okay, so I'm trying to make sure that I don't have that issue occur again before the end of the semester. I don't think that's going to happen. Okay, all right, so let's go ahead and launch into our lecture for today. And so again, this is our second lecture on series, and today we're going to learn another test for when series converge. All right, so remember, a series is an infinite sum, and sometimes infinite sums add up to infinity, and in that case we say the series diverges. But in some cases, infinite sums do not add up to infinity. They add up to a finite value, and those are usually the type of series that we're interested in. And if that's the case, then we say that the series converges. And if it converges, we'd like to know what it converges to. In other words, what the series adds up to. But that's often a really difficult question. Many times we can determine that a series converges, but it's much more difficult to determine what it converges to. Okay, so you understand the distinction between the two. So we may be able to discover that a series does add up to a finite value. We may be able to deduce that without being able to determine what that finite value is that the series converges to, which is sometimes a much harder question. And that's exactly the situation that's going to arise here in a couple of examples. All right, so today I'm going to teach you a new way of determining if a series converges or diverges. This is called the integral test, so it does involve integration. It involves improper integration, in fact. And But so the integral test can tell you if a series converges or diverges, but it does not give you information about if the series converges, what the series converges to, right? So again, if a series converges, that means the series adds up to a finite sum. The integral test can tell you if the series converges, but it doesn't help you understand what that finite sum actually is that the series converges to. So the integral test is useful, but it does have limited power. All right, so let's look at some examples of where the integral test, the so-called integral test, is helpful. All right, so here they are. Here are the questions that we want to know, and it's just the basic question that we often ask about series, right? I'm given a series, and I'm asked, does that series converge or does that series diverge? So does it have a finite sum, okay, or does it actually sum up to infinity? All right. Notice we're not trying to answer here what the series converges to if it does converge, right? We just want to know, does it converge? So that's just a yes or no type of question, right? So here's the first series that we want to look at here. So notice we're adding up terms here from 1 to infinity. Notice the index doesn't begin at 0, it begins at 1 instead of 0. So many times our series index will begin at 0, but here it begins at 1. And here's what the terms of the series look like. They're just n over n squared plus 1. So you take that index, right, and then you divide it by the index squared plus 1. Just to get a better feel for what this series looks like. All right, let's write down some of the terms of the series, right? So let's see. If n is 1, we get 1 over 1 squared plus 1. So that would be 1/2, right? If n is 2, we get 2 over 2 squared plus 1, so that's 2/5, right? If n is 3, we get 3 over 3 squared plus 1, so that's 10, right? And so on and so forth, right? Okay, so there's what the terms of the series look like: 1/2 and 2/5 and 3/10, and so on and so forth, right? And again, we want to know if we want to start adding up 1/2 and 2/5 and 3/10 and keep doing that to infinity, does that add up to a finite number or does that actually go to infinity? Now, remember, in the last notes, right, we learned a simple test to decide if a series diverges, right? And that was called the limit test, right? So we took the limit, right, as the index goes to infinity, correct, of the terms in the series, right? So we looked at the limit. So let's look at the limit as n goes to infinity of these terms. And remember, last time we said that if these terms do not go to 0, in other words, if the individual terms do not get smaller and smaller towards 0, that means that the series would have to diverge, right? Okay. Well, you can already tell it looks like the terms of this series are getting smaller and smaller, right? We start with 1/2, and then we go down to 2/5, which is a little bit less than 1/2, and then we go down to 3/10, which actually is a little bit less than 2/5, because 2/5 is 4/10. So it does look like the terms of the series are getting smaller and smaller, and that has to be the case if the series is going to converge. If the terms are not getting closer and closer to 0, that means the series is going to diverge, right? Okay, so it looks like these terms are getting closer and closer to 0. Let's actually compute this limit, though, formally and see what the limit of the size of the terms is. So to compute this limit, notice I can use L'Hopital's rule here, right? Okay, because as n goes to infinity, of course, the numerator is going to infinity, and n squared plus 1 would also be going to infinity. So notice you have, if you just try plugging infinity in to these numerator and denominator, you get an indeterminate form. You get infinity divided by infinity. And that's an indeterminate form, right? But we can apply L'Hopital's rule to determine this limit by taking the derivative of the numerator and denominator, right? So when we take the derivative of the numerator, we get 1, and when we take the derivative of the denominator, I think I get 2n, right? And so this limit of n over n squared plus 1 is the same as the limit as n goes to infinity of 1 over 2n, but that is clearly 0, right? Okay, because as n gets larger and larger, you're really dividing 1 by a larger and larger number, and that gets closer and closer to 0. So indeed, the terms, just like we observed here, right, the terms are getting closer and closer to 0. So that means that the series has a chance that it's going to converge, right? It's a possibility that it converges. But that doesn't guarantee that the series converges. All this limit test tells us is we know the series has a chance of converging, but we don't know if it actually converges or not. If the if the limit of the terms was not 0, then we would know that the series diverges. Okay, so all we know now from the limit test is, well, it has a chance to converge, but still not sure if it converges or not. Okay. All right. Well, so the limit test here is not that helpful, right? We cannot use that to answer this completely answer this question about convergence or divergence. Now, I want to point out here something that gives me a suspicion that this series may diverge, even though the terms are getting close to 0. I'm still suspicious that the series might diverge still, because this series looks a lot like this series, okay, and this series. And why do I say that they look alike? They're not the same, but why do I say they kind of look alike? Well, notice here, if here you have n over n squared. Now, you can't cancel the n and the n squared because of the plus 1. But if you thought about breaking the rules a little bit, and since plus 1 is not very large, right? If you thought about breaking the rules a little bit and canceling out the n and with the n squared, notice you would end up with essentially 1 over n, correct, right? Because plus 1 is not a very a big number, right? Especially not when n gets really large, right? The plus 1 is kind of negligible. So this series and this series kind of look alike, right? Okay. So we might be led to believe that they sort of behave the same. But this series, we know from the prior notes, we already said this series diverges. We didn't say why it diverges, we just said that it does. This is a famous example of a divergent series, as I mentioned in the prior notes. This is called the harmonic series, and this series is well known to diverge. Okay, so when you add up the reciprocals of integers, not squared, but just the reciprocals of plain integers from 1 to infinity, it turns out that that sum diverges. Okay, and so I'm thinking maybe this series diverges because it's kind of similar to the harmonic series if we think again about canceling the ends, which we really algebraically cannot do, but if we sort of imagine that we do that, right, because we almost can cancel the ends. If the 1 weren't here, we could cancel the ends, right? So if we think about canceling the ends, we get up, this series ends up looking like this series diverges, so I'm thinking, this series may diverge too. Okay, but I'm still not sure of that, right? Okay, so how can I convince myself that this series really does diverge, right? Okay, well, that's where this so-called integral test comes in. So here's a test that's often useful. It does require a little bit of work, but it's often useful for determining if a series diverges or converges. So what the integral test says basically is the following. All right, so it's spelled out here mathematically, but I want to tell you just in practical terms what the integral test does. It says take the terms of your series, right? Okay, and of course those are going to involve your index n, and convert that to a function where the variable is x. All right, so think of the formula for the terms of your series, which usually will involve the index n, okay? Convert that to a function where the variable is x. And then integrate that function from 1 to infinity. It turns out that if this improper integral converges, then the series also converges. But if the improper integral diverges, in other words, if this improper integral turns out to be infinity, then the series also will diverge. Okay. All right. So see, that's kind of cool, right? Okay. Because now we can apply our knowledge of improper integrals, which we learned a couple of sections ago, right? Now we can apply our knowledge of improper integrals, right, to help us determine if a series converges or diverges. Now, there is one other special condition, though. When you convert the terms of before you can apply this test, there's a special condition. When you convert the terms to a function, you have to make sure that that function is decreasing. So it cannot have any hills or valleys in it. The function has to be always decreasing, always going down for x bigger than or equal to 1. All right, so that is one little caveat there, one little warning about when you can use this integral test. It doesn't necessarily always apply. Okay, all right, so let's see if we can apply the integral test to this particular situation. So again, I'm trying to determine, does this series, the sum from n equal 1 to infinity of n over n squared plus 1, does that add up to a finite number? Does it converge or does it diverge? So what I'm going to do is take the terms of the series, okay, and so that formula for the terms of the series, which is n over n squared plus 1, and I'm going to convert that to a function where the variable is x. So I'm going to write this function x over x squared plus 1. Okay, and now I'm going to compute the integral, the improper integral from 1 to infinity. Notice I'm starting at 1 here because that's where the index starts, right? From 1 to infinity of x over x squared plus 1. So we're going to use our knowledge here of integration, right, to compute this improper integral, if we were able to do that, and then see if that improper integral converges. In other words, if this value exists, then that means the series also converges. If this improper integral diverges, in other words, if this quantity turns out to be infinite, then the series also, the original series also diverges. Now, before I actually compute this improper integral, though, again, remember this little caveat here. You have to make sure that this function, x over x squared plus 1, that has to be decreasing, always decreasing, so it can't change direction. It has to always be decreasing for x bigger than or equal to 1, since we're starting to integrate at 1 here. I'm going to check that now with a graph, so just to be careful. So I've actually already made a graph of x over x squared plus 1. There it is. And there's the picture of this function for x bigger than or equal to 1. And what do you notice here? We're in luck, right? Because indeed, it appears that this function is always decreasing, right, as we move out toward infinity on the x-axis. Now we can double check that with calculus by computing the derivative, okay, of x over x squared plus 1, and then making sure, right, that the derivative is always negative, meaning that the function is decreasing, right, for x bigger than or equal to 1. So we don't have to check this graphically. We can check it with calculus, right, by computing derivatives. But I think this visual check is sufficient, right? Okay, it certainly appears to be the case, right, that this function x over x squared plus 1 is always decreasing, always going down, right, for x bigger than or equal to 1. So that's good news for us. That means that the integral test applies. So if this, again, if we compute this improper integral, and this improper integral converges, then the original series converges. If it diverges, then the original series diverges. All right, so, well, we have to do it now. So let's compute this improper integral. So now we're pretty skilled at doing this, right? Now we have to convert this to a limit, right? So we'll take the limit as b goes to infinity of this definite integral from 1 to b, right, of x over x squared plus 1. And now to compute this definite integral from 1 to b, right, I need to find the antiderivative of x over x squared plus 1. Let's see if I left myself enough room here to do this. Oh, I think I did, right? Okay, so let's find the antiderivative of x over x squared plus 1, and then we'll use that, right, to compute this definite integral. So how do we find this antiderivative of x over x squared plus 1? I think we're going to do this by substitution. Let's let u be x squared plus 1, and if we do that, that means du dx is 2x, right, which is very close to x, so which is in the numerator here. So that gives me a good feeling, right, that I'm going to be able to integrate this by substitution. Let's see, what is dx equal to then? Dx would be equal to what? Du over 2x, right? And now let's do the substitution. So I have the antiderivative of x over u times dx, but dx is du over 2x, right? And so the x's will cancel nicely, right? And we can factor out a 1/2 in front here. So I have 1/2 times the antiderivative of du over u, your favorite antiderivative, right? Because that is going to be natural log of the absolute value of u, right? But u, of course, is x squared plus 1. But x squared plus 1 is always going to be positive, because even if x is negative, when you square it, it will be non-negative, right? And then when you add 1, that makes it definitely positive, correct? So we can drop the absolute values. So I only have to write 1/2 times the natural log of x squared plus 1. There's the antiderivative that I can use to evaluate my definite integral, right? So let's fill that in. So we have the limit as b goes to infinity of, let's see, what is it here? 1/2 times the natural log of x squared plus 1, right, evaluated from 1 to b, right? I guess I can take the 1/2 now out in front of the limit, so I have 1/2 times the limit as b goes to infinity of, now let's plug in our limits of integration. So I have natural log of, it looks like b squared plus 1, and then minus the natural log of 1 squared plus 1, which is 2, right? Well, as b goes to infinity, the natural log of b squared plus 1 is going to be getting larger and larger, okay? So this is going to be getting infinitely large, and natural log of 2, of course, is whatever it is. It's natural log of 2. It's not a very large number. It's a little bit less than 1, I think, okay? So make a long story short here, this limit is going to be infinity, because natural log of b squared plus 1 is going to infinity as b goes to infinity, and of course natural log of 2 is just a constant. So you end up with this limit being 1/2 times infinity, which is infinity, of course. So that means that our improper integral diverges, right? Okay, it doesn't have a does not have a finite value. So that means the original series also is going to diverge. So there's the answer to the question. All right, so see, that took a little bit of work, right? But we were able to discover it, right? This series does not add up to a finite number. When you add up 1/2 plus 2/5 plus 3/10, et cetera, et cetera, I think the next term is 4/17, et cetera, then those numbers do not add up to a finite number. They actually add up to infinity. This series diverges. Okay, all right, so there's our first application of the integral test, right? So we were able to discover that indeed this series diverges, like it's sort of a similar series, the harmonic series, right, diverges. And I said I thought these two series were kind of similar to each other. Well, this series also diverges, right, just like the harmonic series diverges. Okay. let's try another example. All right, so this one is kind of similar to the first example. See, here I had n over n squared plus 1, but here I have just 1 over n squared plus 1. Okay, and so I don't have the n in the numerator, right? Okay, so it's slightly different. So if we look at the terms of this series, what would they be? Let's see, you would have what? 1/2 again, plus now 1/5. When n is 2, you get 2 squared plus 1, which is 5, right? Plus 1/10, plus 1/17, plus etc. So similar, right, series to example A, but notice the terms are a little bit smaller. See, in the previous example, we had 1/2 plus 2/5 plus 3/10 plus 4/17. Here we just have 1/2 plus 1/5, not 2/5, plus 1/10, not 3/10, plus 1/17, not 4/17. And so now we're wondering, does this converge or does this diverge? I want you to notice this series kind of looks like this one. Right? Okay? Because if you notice, when n gets really large, this 1 sort of becomes negligible, right? Okay? So this series is very similar to just the series where you're adding up 1 over n squared, okay? Right? So probably the behavior of these series is quite similar, right? But I don't know. I don't know from last time. I don't know if this series converges 1 over n squared. I don't know if that series converges or diverges. I knew that 1 over n to the first power diverges. That's a famous example of a divergent series. But this series we're not quite certain of yet. So I don't know what to expect from the sum of 1 over n squared plus 1. Comparing it to 1 over n squared doesn't really help me because I'm not sure if this series converges or diverges either yet. All right, but again, we're going to try here using the integral test, okay, and see if that will help us. So again, I'm going to take the formula for the terms of the series, right, 1 over n squared plus 1, and I'm going to convert those to a function with the variable x, 1 over x squared plus 1, right? And then I'm going to think about, what is the improper integral, right? So what's the integral from 1 to infinity of 1 over x squared plus 1? And if that improper integral converges, then the original series converges. If that improper integral diverges, then the original series will diverge. But I have to, again, make one check, right? I have to make sure that this function 1 over x squared plus 1 is always decreasing when x is bigger than or equal to 1. So I can check that with calculus again by taking the derivative of 1 over x squared plus 1. But I'm going to check this just informally with a graph because I've already got almost this graph built. All right, so I'm going to change the x here in my previous graph to 1, and then let's look at the graph of that function, and starting at 1, right? Well, there it is, and I think it's pretty clear, right? Yeah, for sure, right? When x gets larger, right, 1 over x squared plus 1 is always decreasing, right? Okay, it's doesn't have any peaks or valleys in it, right? It's just going straight down, right? Okay, well, not straight down, but it's definitely decreasing, right, for x bigger than or equal to 1. So that means that my integral test is valid here, right? I am free to use the integral test. So if I can determine this improper integral, then I'll know what happens to this series. All right, so let's convert that improper integral to a limit, right? So we take the limit as b goes to infinity of the definite integral from 1 to b of 1 over x squared plus 1, right? And now I need to, just like before, right, I need to see if I can find what is the antiderivative of 1 over x squared plus 1. And now that you've gotten so good at integration, right, you're going to immediately recognize how to find the antiderivative of 1 over x squared plus 1, right? You're not going to try to use substitution, correct? Right, okay. You're not going to try to use partial fractions, right, to integrate 1 over x squared plus 1. This can be integrated easily using the arctangent function, right? So the antiderivative of 1 over x squared plus 1 is just nicely here. It's the arctangent of x. Just that simple. See, the a value here is 1, right? Because 1 is 1 squared, and the u here is x. So what you really have here is 1 over the sum of 2 squares, right? And you know you can find the antiderivative of 1 over the sum of 2 squares, right, by using the arctangent function. So the antiderivative turns out to be, well, it's 1 over 1, because a is 1, right, times the arctangent of x over 1, because a is 1, but, of course, that just simplifies to arctangent of x. Let me remind you of this. This is 1 over a, right, times the arctangent of u over a, but u is x, and since a is 1, this just turns out to be arctangent of x. Okay, so there we have it, right? All I have to do now is use that antiderivative, right? And then in this definite integral, and then take my limit, right? So I have the limit as b goes to infinity of arc tangent of b, right, minus the arc tangent of 1. And now we have to remember a little bit about the arctangent function, correct? As b goes to infinity, right, remember the arctangent of, as b goes to infinity, remember the arctangent of b. What's happening to the arctangent as your input goes to infinity? Remember that is going to pi over 2. So we've seen that now several times, right? Right, as the input goes to infinity, the arctangent is going to pi over 2, and the arctangent of 1 is pi over 4, because the sine and cosine are the same at pi over 4, right? So sine of pi over 4 divided by cosine of pi over 4 is going to be 1, and so the arctangent of 1 will be pi over 4. So you end up here with, a really nice calculation. You just end up with pi over 4. So, this improper integral is pi over 4. It's not infinity. So that means that this improper integral converges, right? And so, that tells me that this original series also converges. So these numbers add up to a finite sum. They do not add up to infinity. They add up to a finite sum. So slightly different from the prior example. See, just taking that in and changing it to 1, change that divergent series to a convergent series now. However, I do not know, so here's where you have to be really careful. Don't jump to conclusions. I do not know that the sum of this series, even though I know it has a finite sum, I do not know that it's pi over 4. So do not say that the sum of 1 over n squared plus 1 is pi over 4. Okay, all right. All I know is that the series converges. The improper integral and what the series converge to do not have to be the same value. Okay, so this series does converge, but I don't know that it converges to pi over 4. All I know now is that it converges. Fortunately, that's all I was asked, right? Okay, so that's how the integral test works, right? See, it's very handy when it works. All right, now we can take the integral test and we can convert that to actually a simple formula that you can use to check the convergence or divergence of certain types of series very quickly. And this certain types of series are called P-series. So we've already seen one type of series called the geometric series, right, back in the prior notes. And so this is a slightly different type of series called a P-series. And the integral test can tell us immediately whether a P-series converges or diverges. So we're going to take a look at examples of P-series here in just a second. Let me pause here for a moment, though, before we take a look at P-series. Okay, so let's resume and let's look at this new type of series that's called a P-series. So if you have a series of this form, notice, so you're taking the sum. Notice you're beginning the index at 1, not at 0. You're beginning the index at 1 to infinity, and your terms have this form. So you have the reciprocal of the index, right, raised to a power, right? So your index is being raised to a power. If that's what the terms in your series look like, then that's called a P-series, right? So if you expand what a P-series looks like and write out the terms, you have, again, you would have the index to the 1 over 1 to the power, 1 over 2 to the power, 1 over 3 to the power, and so forth, right? Notice that in a P-series, the power here that's a constant. That remains fixed. What's changing is the base. The base is the same as the index. So it's the base of the power that's changing. So we've already seen a famous example of a P-series here. When this power is 1, that would correspond to this. That would correspond to this series. Okay, when the power is 1, and that is the that's the harmonic series that we already mentioned earlier in the lecture. Okay, right? But if, for instance, the power is, for instance, if the power is 2, if P is 2, then your series looks like this, right? 1 over n squared. So you would have 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus etc. Okay, but again, the sort of the format of the terms in a P-series is the same, right? It's always 1 over the index raised to a power, and the power stays the same, right, in every denominator. The only thing that's changing is the index. Now, let me remind you, we've already looked at another type of series that occurs frequently. P-series occur frequently in practice, so that's why we're sort of singling them out. But we already mentioned another type of series that occurs frequently in practice. That's called the geometric series. And so we saw that in the prior notes, right? The geometric series look like this, have this form. And I just wanted to mention what the difference is. So what's the difference between a P-series and a geometric series? And the difference is very obvious, right? In a P-series, notice you have the index changing, but the power is fixed, right? So it's always 1 over, and then the index raised to always the same power. In a geometric series, you also have powers, right? Okay, in your terms. But notice the base is fixed, right? And it's the exponent, the power, that's changing in a geometric series. But in a P-series, it's the opposite, right? It's the base that's changing, and the power remains fixed. But in a geometric series, the base is always the same, but the power is increasing, right? Here's an example of a geometric series. If you have 1/2 raised to the nth power, take the sum of that to infinity, that's called the geometric series. If you, of course, 1/2 to the nth power is the same as 1/2 to the nth power, right? So you see, the base is, in all the terms of this series, the base is always 2, but the power is getting larger and larger, right? Okay, because the power is the same as the index. So in a geometric series, base is the same, but the power is changing. In a p-series, this is an example, 1/n² is an example of a p-series. Notice it's exactly flipped, right? The base is changing, right? Because the base is the same as the index, but the power always stays the same, okay? It's always, whatever value you choose there. It could be 2, it could be 1, it could be anything, right? But the power stays the same. The base changes. But in a geometric series, base stays the same. The power is changing. Okay. All right. So, there's that fundamental difference between geometric series and p-series, or you can also call these power series if you want to, because the p is short for power. And what do we know about p-series? We know a lot, okay? And so that is summarized in this theorem, okay? And very easy to apply, okay? So here's what the theorem says. So if you have a p-series, right, okay? So again, base is changing, but the power is always this value p, right? It always stays the same. Then if that power is bigger than 1, then the series converges, okay? So if the power has to be bigger than 1, cannot be equal to 1, but if the power is bigger than 1, then the series converges, right? On the other hand, if the power is 1 or less all the way to 0, you don't have p ever equaling 0. But if the power is a fractional value between 0 and 1, including 1, then you know that the series diverges. So the larger the power, the series converges. The smaller the power, the series diverges. And the breakpoint is right at 1. Okay, so power is bigger than 1, form the p-series, it converges. Power is less than 1, less than or equal to 1, I should say, form the terms of the p-series, then the series diverges, right? It doesn't add up to a finite value. Notice this theorem does not tell you, though, what the sum of the p-series is, okay? It just tells you, does it converge or does it diverge? But it doesn't tell you what the actual sum is, right? So, both of these a series that we already saw in the prior two examples, right? 1/n to the first power and 1/n². See, these are both examples of p-series, right? This is the harmonic series, as I said now numerous times, right? When the power is 1, this is called the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4. And we know that diverges because the power is equal to 1. See, when the power is equal to 1, the series diverges according to this theorem. Again, this theorem comes from the integral test. That's how you can derive this theorem. But in this series, 1/n², the power is 2, right? Because you have 1/1², 1/2², 1/3². Then we know that this series converges. We don't exactly know what it converges to, but we know this series converges because the p value, the power value, is bigger than 1. Oh, so we just learned something, right? 1/n², that series converges, okay? We didn't know that earlier, but now we do, okay? And this series, of course, the harmonic series, diverges. I think I have this written down, what I just said, as examples, right? Okay, so here's the harmonic series, right? Okay, and we want to know, does the harmonic series converge or diverge? Well, since the power here of the index is 1, right? Then and you're adding up terms, right? Where which in this series, right, the terms are reciprocals of the index raised to a power, and the power is 1. Since 1 is less than or equal to 1, that means that this series diverges, right? And again, as I said before, right? This is called the harmonic series. So the harmonic series diverges. On the other hand, when we have reciprocals of the index squared, okay, reciprocals of the index squared, so 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, this is going to converge, right? Because here, this is a p-series with p equals 2, which is bigger than 1, right? And so we know the series converges, but we do not know what the series converges to, right? So we know these terms, 1, this is 1, plus 1/4, plus 1/9, plus 1/16, plus 1/25, plus 1/36, plus 1/49, right? The reciprocals of the sum of the reciprocals of squares, we know those numbers add up to a finite value, but so far we don't know what that is. I will tell you that sum is difficult to determine, and it wasn't actually determined what the sum of this series is until probably the 1800s. It turns out to be, I think, if I'm writing this down right, a really strange number. It turns out to be pi squared over 6. I think that's right. Okay, wow, who would have guessed that, right? Okay, but all we know is that according to our p-series test, right, all we know is that this series converges. So if you take the sum of from 1 to infinity of 1 over n to the 1.0001, right? Notice these two series are very similar, because this is 1 over n to the first power. Here's 1 over n to the 1.0001 power, right? So these two series has to be very similar, but notice, although they're similar, they're different in one major way. This series is going to converge, right? This series converges where this series diverges, right? Why? Because the p-value here is 1.0001, right? And that is slightly bigger than 1. But it doesn't matter if it's only slightly bigger than 1. As long as it's bigger than 1, that means that the series converges. So this p-series will converge, whereas the harmonic series diverges. Well, lots of series we encounter in practice are p-series, so this is a really useful and very quick to apply, right, test. Okay, so if you recognize that the series that you're given is a p-series, then all you have to look at is that power, and you can decide if the series converges or diverges. But make sure you're distinguishing p-series from geometric series, right? Okay, because they're fundamentally different and they have different behaviors. But we studied geometric series back in the prior notes. Okay. Now, still lots of series that we don't know whether they converge or diverge. Here's a famous example: 1 over n times the natural log of n. By the way, we're starting the index here at 2. You can't start at 1 because natural log of 1 is 0, so you'd end up here with 1 over 0. So here we're starting the index at 2. So we're wondering, does this series converge or diverge? Don't know yet. Okay, the series test, the p-series test does not apply in this case. Okay, so and this is not a geometric series either. So still, there are lots of series that we can't determine if they converge or diverge just using the tests that were given so far. Okay, so that's all I'm going to say about p-series, all right, and the integral test. So we're done with our notes for today, and then on Wednesday we're going to learn but again, this Wednesday's lecture will not be on the exam for Monday, right? There's just one additional homework that we're going to have that's due at the time of the final exam. So it'll be problems for that homework that I'll be talking about Wednesday. And these are two additional tests that you can use to determine if a series converges or diverges, because you already mentioned that although the integral test is very powerful, doesn't always help us. So we need other tools to decide if a series converges or diverges. And there are lots of other tests, actually. We're going to learn just a couple of them that are easy to apply on Wednesday. All right, so stay safe until Wednesday. Be keeping up with your homework. So you will have a couple of homeworks due this week, right? So make sure you're hanging in there on those homeworks. There's one due on Tuesday, and then another one due on Wednesday. So they're coming close together, but they're not lengthy homework assignments, either one of them. All right, so and I will see you again on Wednesday then, April 22nd.